Hello, in this video I want to talk about the Segre chart, S-E-G-R-E, Segre. The Segre chart is not in the A-level syllabus, but I think it's quite fun, so let's do it. The Segre chart is basically a plot of different nuclides. On the horizontal axis, we have increasing neutron number. On the vertical axis, we have increasing proton number. So every pixel here represents one nuclide. Let me zoom in so that you have a closer look. Let me click on this pixel here. So this is the Lead-203 nuclide. It's unstable. It has a half-life of don't know how many thousand seconds. Let me click on another one. So this is the Polonium-207. It's also unstable and the half-life is given here. Notice the nuclides are color-coded. Let me zoom out again. Now those that are colored black are the stable nuclides. So all the rest are the Bohose nuclides, the unstable nuclides. Yes, out of the 2,500 known nuclides, only about 300 are stable. I'm sure you have noticed that they kind of line up along this line here. In fact, this line is called the Valley of Stability. The largest nuclide that's stable, I think, is the Lead-208. Let me confirm, yeah? So this one, yeah, that's right. Lead-208, that's the largest stable nuclide. Any nuclide that's larger than Lead-208, so anything that has more than 208 nucleons, are confirmed unstable. So what do unstable nuclides do? They undergo radioactive decay. So again, the decay is color-coded. You can see the color codings here. So you can see a lot of these nuclides here undergo alpha decay. These are the ones that have too many protons and too many neutrons. So I guess the fastest way to get rid of excess protons and neutrons is to throw out alpha particles. So you see a lot of yellow color nuclides here. Those are the ones that emit alpha particles. Now those below the valley of stability, the green color ones, these are the ones that have too many neutrons and too few protons. So what do? They undergo beta decay. So by converting a neutron into a proton and a beta particle, they kind of nudge themselves towards the valley of stability. So those that are above the valley of stability, the blue color ones, these people have too many protons but too few neutrons. So they undergo positive beta decay. So they throw out positrons instead of electrons. But the beta positive decay is not in your A-level syllabus, yeah? Let's zoom back in to the heavy nuclei here. Now let me look for uranium. Uranium has 92 protons, right? Okay, let's go down. Here. Yeah, there's a uranium, and so is this, yeah? Anything along the same horizontal row are all uraniums. Now, if you are born a uranium nuclide, you're unstable, right? So what do? You undergo radioactive decay, which will turn you into another nuclide, which is also unstable. So we have what is known as a decay series. Through a series of radioactive decay, you keep moving yourself towards the valley of stability, until eventually you become one of the stable nuclei. Let's switch to another applet here. This one will show you a few famous decay series. So the thorium series is the one that starts with thorium-232. Thorium-232 is found naturally in the Earth's crust. So it's found in granite, concrete. Basically, it's found in the walls of your home, yeah? As for the neptunium, neptunium is not a natural element. It's actually a byproduct of the fission of plutonium. As for uranium, so this one is uranium-238, and there's another decay series that starts from uranium-235. Again, these are naturally found in the Earth's crust. Okay, let's try the thorium series and see how the thorium-232 works its way towards becoming stable. So starting from thorium-232, it undergoes an alpha decay to become radium-228. Remember, the horizontal axis is the number of neutrons and the vertical axis is the number of protons. So when you undergo an alpha decay, you lose 2 protons and 2 neutrons. That's why you go down 2 steps and you go left 2 steps to end up at radium-228. So from radium-228, you undergo a beta decay to become actinium-228. Remember, during a beta decay, a neutron is converted into a proton and a beta particle, of course. So you lost one neutron, but you gain a proton. That's why you move 1 step left and then 1 step up. Then from actinium-228, you undergo a beta decay to become thorium-228. How come we are thorium again? Yeah, that's right. But you were the thorium-232 isotope. Now you are the thorium-228 isotopes. Altogether, you have lost 4 neutrons. You lost 2 protons during the alpha decay, but you gain back 2 protons in the 2 beta decays. So you are back to being thorium. Then from thorium, you undergo a alpha decay to become radon-228. And from radium-228, you undergo yet another alpha decay to become radon-220. Radon is a gas. That's when you get radon gas seeping out of the granite, which makes our atmosphere radioactive. Now radon-220 will undergo an alpha decay to become polonium-216. Are we done yet? No, polonium-216 is also not stable. It will undergo yet another alpha decay to become lead-212, which will undergo a beta decay to become bismuth-212, which will undergo yet another beta decay to become polonium-212. So you see, your polonium yet again. After one alpha decay and two beta decays, you're always back to the same element. From polonium-212, you undergo an alpha decay to become lead-208, which is a stable nucleus. So this is the end of your journey. The nucleus has finally found peace within itself and live on happily ever after. Alright, that's all. Ta-ta!